Okay, so today we will look into radial inflow turbine. The best known radial inflow turbine is usually we can see in turbocharger in car. Modern car nowadays usually use turbocharger to increase engine power delivery for a compact engine design. Okay, other than turbocharger in car, radial inflow turbine is also used in aircraft engine, and also in some industries such as natural gas processing or air liquefaction or geothermal energy production. Okay, in automotive application, burn gases from the engine exhaust manifold are directed into a radial inflow turbine of the turbocharger. Okay, radial flow turbine usually use a volute. A volute is a casing, like you can see in this figure, a casing where the inlet is big and the outlet, the diameter decrease gradually to the outlet and then go inside the stator vane and the rotor blade. Okay, so radial inflow turbine, as the name implies, the fluid enter the turbine radially, as you can see in this schematic diagram. It's enter the turbine radially and then exit the turbine axially. Okay, it will exit the turbine. If you can see the screen, it will exit like the direction will go inside the screen. Okay, it's enter from here, the gas enter radially from this inlet, go round the volute and exit axially from the volute and go inside the screen. Okay, that's why the name radial inflow turbine. Okay, only the inflow radially, but the outflow is axial. Okay, a sketch of the turbine. You can see in this left figure at the bottom here. Okay, the flow or the fluid will enter the volute through this and go inside the volute and will exit here. Okay, it enter radially and exit axially. If we look into the velocity diagram of a radial inflow turbine, it's actually very much similar with compressor. Okay, it's very much similar with centrifugal compressor. And the shape of the turbine is also very much similar with centrifugal compressors. But the function is, if the compressor compress air, but turbine expand the gas. Okay, so we can see this is the velocity triangle at the inlet of a radial inflow turbine, and this is the velocity triangle at the outlet of a radial inflow turbine. Okay, if we look into this triangle velocity, we can calculate the work delivered by the turbine. Okay. First of all, we can write the work delivered by the turbine in terms of kinetic energies. Okay. Using this expression, work equal 1 over 2 V2 squared minus V3 squared plus 1 over 2 U2 squared minus U3 squared plus 1 over 2 W3 squared minus W2 squared. If we look carefully into this equation, we can understand that by increasing V2, we can increase the we can also increase the work delivered by the turbine. Okay, increasing V2 will increase the work delivered by turbine. Okay, we can increase V2 by orientating the stator blades such that the flow enters the rotor at a large nozzle angle alpha 2. Okay. Similarly, a small value of W2, can also increase the work delivered by the turbine. And this can be obtained by directing the relative velocity radially inward the inlet. Okay, the same reasoning leads to a design in which the exit velocity V3 is axial and therefore as small as possible, and in which the relative velocity W3 is large. Okay. Okay, this can be obtained by making the magnitude of the flow angle of the relative velocity beta 3 as large as possible. Okay, and finally, what we can say from this equation, from the work delivered in terms of kinetic energies equation, is that we can have, or we can optimize, or we can get a maximum work delivered by increasing U2 and decreasing U3. Okay, so we can also write work delivered by a radial inflow turbine in terms of in VU2 and VU3 using this expression. Okay, so the first expression here is work delivered in terms of kinetic energies, and usually we can write work delivered by turbine using this expression, using just velocity. Okay. Okay, in this expression, we can see a velocity called VU2 and VU3. Okay, VU3 here should be small or smaller than VU2. Okay, similarly, U2 should be large or larger than U3, which means that the ratio R2 over R3 is going to be large. Okay, it's going to be large, and work could be increased. A radial inflow turbine could be increased by making VU3 negative, which in the end will sum these two terms. Okay, but this would also increase the absolute value of beta 3. and the exit relative Mach number might become too large. If the Mach number is too large at the exit, the flow will choke, which means the flow cannot exit the turbine. Okay, it's undesirable, but theoretically, we can increase the work delivered by radial inflow turbine by making the value of VU3 negative by increasing the angle beta 3. But practically, it's not very practical. Okay. Okay, if the exit velocity, if the exit swirl velocity is eliminated in this in this equation, we will end up with only the first term, which is U2 multiplied by VU2. Which means the exit velocity is cancelled. Okay. Since the blade speed is small at the hub, if the exit velocity is designed to be uniform across the exit plane, then the flow angle and therefore also the blade angle must be turned more at the shroud than at the hub. Okay, so we can calculate U3 or the blade speed U3 using this equation R3 omega. Since the blade speed U3, the blade speed U3 is smallest at the hub, if the exit velocity is designed to be uniform across the exit plane, then the flow angle and therefore also the blade angle must be turned more at the shroud than at the hub. Okay, U3 can be calculated using this equation. U3 equal R3 omega. And we also can calculate the work delivered by turbine using this expression. W equal Cp T01 minus T03. And this equation, if we can rearrange this equation into this arrangement, which will give SW. The SW is the equation for specific work intensity. Okay, specific work intensity. If we rearrange the work delivered by turbine or radial inflow turbine in this term, we rearrange this equation to get SW, which is the specific work intensity. Okay, so specific work intensity is equal W over CP or capital W dot over M dot CP, which give the power ratio. Okay, the power ratio of the turbine. Okay, so from work delivered by a turbine, by cleverly rearrange the equation, we can get the equation for power ratio. Okay, if the exit kinetic energy, looking at the power ratio equation, if the exit kinetic energy is wasted, as is often the case in radial inflow turbine, it is appropriate to use the total to static efficiency as the proper measure of efficiency. Okay, from this condition, we can calculate the efficiency of the turbine or the total to static efficiency of the turbine using this equation. T01 minus T03 over T01 minus T3SS. Or we can rearrange this equation, which equal 1 minus T03 over T01 over 1 minus T3SS over T01. Or we can also calculate the total to static efficiency of radial inflow turbine using alternative expression, this one, which equal to 1 minus T03 over T01 over 1 minus P3 over P01. This is the pressure ratio. Okay, this is the using pressure ratio powered by gamma minus 1 over gamma. Okay, okay, from this expression, we can get, we can solve pressure ratio using this equation. Okay, pressure ratio can also be calculated using the specific work intensity value. Okay, P01 over P03 equal 1 minus SW over eta TS, or the total to static efficiency, powered by minus gamma over gamma minus 1. Okay, radial inflow turbine, the best way to evaluate the efficiency of radial inflow turbine is to use the total to static efficiency. Okay, okay, the expression for work now can be written as W equal CP T01 SW. Okay, until now we have looked into various expression to calculate the work delivered by radial inflow turbine. Okay, which shows that it's depend on what information we have, so that we can calculate the work delivered by a radial inflow turbine using which equation. So it's depend on what information we have. So we have to choose which equation suitable for calculating the work delivered by radial inflow turbine. Okay, the graph on the right hand side shows the pressure ratio for a gas as a function of power ratio, or total to static efficiency equal 0.82, total to static efficiency equal to 1. Okay, what we can see here is that the higher the specific the specific work delivered by turbine will give a higher pressure ratio. Okay, higher specific work value will give higher pressure ratio. So in other way to say this, that to get more work delivered by radial inflow turbine, we have to get a higher pressure ratio. But higher pressure ratio always come with a risk to damage the turbine. Okay. We want to get as much work as possible from turbine, but we don't want to damage the turbine. Okay, that's the design aspect of turbine. Okay, for isentropic flow condition, the work delivered by radial inflow turbine can also be calculated using another expression of work, which is equal to H01 minus H3SS, which equal to 1 over 2 V naught squared. In this equation, V naught is called the spouting velocity. Okay, V naught is known as spouting velocity. Okay, the kinetic energy associated with and spouting velocity is a convenient replacement for the maximum work that this turbine can deliver. This equation can also be interpreted as defining what velocity would be reached in a frictionless nozzle as the flow expands from pressure P01 to the exit static pressure P3. Okay, expand from P01 to P3. Okay, the equation for work can now be written as 1 over 2 V naught 2 equal CP T01 in bracket 1 minus T3SS over T01. If we rearrange this equation, we can get this equation in terms of pressure ratio, which gives V naught squared over 2CP T01 equal 1 minus P3 over P01 powered by gamma minus 1 over gamma. Okay, and the total to static efficiency can now be calculated using W over WS equal 2U2 squared over V naught squared. Okay, now we have another expression for work delivered by radial inflow turbine, and also another expression for total to static efficiency for radial inflow turbine. But this expression is only can be used for isentropic flow condition. Okay, this equation can only be used for isentropic flow condition. It's not a general expression that can be used all the time. Okay. Okay, so that is pretty much the fundamental aspect that you need to know, or the main equation or expression that you need to understand for radial inflow turbine. Now we want to look into an example so that you can get more understanding on how to use those equations. Okay, looking at this example, a radial inflow turbine with radial blades at the inlet operates at 62,000 RPM. Its inlet diameter is D2 equal 12.6 centimeters. The gases enter the blades radially and leave without exit swirl, which means leave purely axial. Okay, the supply temperature is T01 equal 1150 Kelvin. The pressure ratio of the turbine is P01 over P3 equal 2, and the mass flow rate is m dot equal 0.31 kilogram per second. The ratio of specific heats is gamma equal 1.35. and the gas constant is R equal to 87 joule per kilogram Kelvin. Find the ratio U2 over V naught, in which V naught is the spouting velocity, the total to static efficiency, and the power delivered by the turbine. Okay, before we can solve this problem, we look into this specific heat equation. Okay, Cp, okay, this is a general equation. Cp equal gamma R over gamma minus 1. Okay, you should know this equation already in thermodynamics. Okay, so we can use values that given in the equation to calculate the specific heat. Okay, which gamma equal 1.35 and R, or the gas constant, is equal to 87. Okay, using those values, we can calculate specific heat. Will give a value of 1107 joule per kilogram Kelvin. Okay, next, the isentropic static temperature at the exit is T3SS. Okay, T3SS is equal, we don't know the isentropic static temperature at the exit, but we can calculate T3SS using values that given in the equation, in the question. Okay, so T3SS is equal to T01 P3 over P1, or the pressure ratio, powered by gamma minus 1 over gamma. Okay, in the question, we know the value of T01 and also the value of pressure ratio and the value of gamma. So we plug in those values inside this equation, we will get the isentropic static temperature at the exit is equal to 960.84 Kelvin. Okay. Okay, now we can calculate the isentropic work delivered by the turbine using one of the work expression that we have seen before this, which is Ws equals Cp in bracket T01 minus T3SS. So we already calculated Cp and we know T01 from the questions, and we have calculated T3SS. So we just plug in all those value inside this equation. We will get the isentropic work delivered by this turbine is equal to 209.40 kilojoule per kilogram. And the spouting velocity is V naught equal square root of 2 Ws, or work delivered, or isentropic work delivered by the turbine. So we just use the value that we have calculated here inside this equation to get the spouting velocity, which equal to 647.1 meter per second. And now we can calculate the blade speed at the inlet using this equation, which is U2, or the blade speed at the inlet, equal R2 omega. Okay, R2 is given in the question, and omega we can calculate from the RPM of the turbine. So R2 is equal to 12.6, and omega we can calculate from the RPM of the turbine. So we can get the blade speed is equal to 409 0.0 meter per second. So that the ratio, so now we want to get what the question asks for, which is the ratio U2 over V naught. Okay, we have the value of V naught and we have the value of U2. So we can calculate the ratio of these two velocities, which becomes 0.632. Okay, so the ratio of U2 over V naught is equal to 0.632. Okay, moving on to the next question, which we want to calculate the total to static efficiency. Okay, total to static efficiency of an isentropic condition radial inflow turbine can be calculated using this expression, okay, which equal to work over isentropic work. Okay, WS we have calculated when we want to get the ratio of velocities U2 over V naught. Now we have to get the value, or we have to calculate the value of work delivered by the turbine. Okay, work delivered by the turbine is actually equal to U2 squared. U2 squared. So we have calculated U2 before this, and we just multiply U2 with U2, and we will get the value of work for this turbine is equal to 167.31 kilojoule per kilogram. Okay, now we can calculate the total to static efficiency of the turbine by plugging in this value inside this equation. Okay, so 167.31 over 209.40, we will get the total to static efficiency of this turbine is equal to 0.799. 0.799 or 79%, okay, of the energy of the input energy is converted into can be converted into useful energy. Okay, 79.9% of input energy is useful. Only 11 no 21 or 21%, about 21% of the input energy is lost. Okay, this is a quite efficient turbine. Okay, and lastly is the power delivered by the turbine. Okay, the power delivered by the turbine can be calculated using this equation, using the mass flow rate multiplied by the work delivered by turbine. Okay, mass flow rate is given in the question, and the work delivered by the turbine we just calculated here. So 0.31 multiplied by 167.31, we get the power delivered by this turbine is equal to 51.87 kilowatt. Okay, so we have gone through an example of radial inflow turbine. So hopefully now you can understand how we can use the equation to solve the equation and expressions that we have learned to solve problem concerning a radial inflow turbine. Okay, most of the equation you have to you have to memorize the equation. Okay, you have to memorize the equation in order to solve the problem. Some equation is quite a general equation. Some equation is derived from general equation. Okay, so remember that I before this I have asked you to try to derive some equation. The practice to derive equation is important so that we don't have to memorize all equations. We just have to know how to derive the equation from the fundamental equation. Okay, if you know how to derive equation from a basic equation, then you don't have to memorize a lot of equation. If you don't know how to derive the equation, then you have to memorize many equations.